So welcome to my, as you said last, my third and final lecture here on augmentation. So today I want to talk about the weighted version of tree augmentation, but maybe before doing so, there's one more thing I want to highlight about the end of what we did last time. So this goes back to comment of Laura. I think that one thing I didn't highlight enough probably. So I mentioned at the very end, this result is 1393 result for tap you can obtain. So I showed the 1.5 plus epsilon approximation during the lecture, and said you can then improve it by a technique that improves one of these two rounding steps that we discussed. And actually it also extends to connectivity augmentation. So maybe, so this extension from tap to connectivity augmentation is actually quite non-trivial. So it's not just like a simple observation, but there's quite a couple of new ingredients. The main reason is that maybe in tab it's kind of much easier to understand how much you covered already, because you can describe a solution by covering the edges of the tree. So this is one-to-one correspondence between min cuts, which are one cuts, and tree edges. That's not true for connectivity augmentation, where we can reduce the problem to cactus augmentation, as we discussed, but there, of course, the cut structure is more complicated. Also, you may, of course, have square many cuts compared to, in the order of square many cuts, compared to the size of your graph. So here, even some basic questions, like how do you cover all the cuts cheaply that are heavily covered by an LP solution, become more interesting. Actually, that question can be mapped to a rectangle hitting problem. And also the rounding procedures have to be adjusted. On a high level, one does follow what I showed to you during last lecture, but there's quite a couple of new ingredients. So please keep it in mind. So it's kind of a technical, it remains somewhat technical to do that at that step. Good. And now I would like to move over to the weighted version of tree augmentation. Let me just start with the outline. So what I want to do today, and as I may have mentioned at the beginning, I turned out to be a little bit too over-ambitious in terms of what I can cover, so I will maybe have to skip a few parts, at least some proofs, but I think I should be able to convey the main message. So the main thing here is to go to this problem of finding better than two approximations for weighted tap. And this has been open for a couple of decades, and now only this year we found first approaches that achieve a better than two approximation, and actually two of them. And one of them is, so the second one will be a 1.5 plus epsilon approximation. And even though it's the same factor as what you have seen for the unweighted version, it's a completely different approach. It's not LP based, it's combinatorial, and it uses a local search approach. But I want to go actually in three steps today. First, I want to show a relative greedy algorithm that will already beat the factor 2 and highlight a lot of the main ingredients we need. So you'll get a 1 plus natural logarithm of 2 approximation, and so that you don't have to compute this in your head. That is roughly, or for small enough epsilon, is actually smaller than 1.7, so it's already clearly below factor 2. And this is based on a structural result, which we call the decomposition theorem. And then using that, we can actually further improve things through a local search procedure. And also this idea of having this relative greedy first, and then improving to the local search procedure, turned out to be an idea that is applicable beyond tap. So they can also do, we'll mention that at the end, one can actually get an algorithm for the Steiner tree problem that matches the currently best procedure, which is a log4 approximation, log4 plus epsilon, be precise. One can do something similar in Steiner tree. People use already relative greedy. Actually, a technique started with the Steiner tree problem, and there too one can obtain the best factor in that context that's known. So it's kind of maybe an idea that is more general than just for tab. It's also one more reason why I would like to go through those three steps. Good. Let's start with the relative greedy procedure. And maybe also one thing I want to repeat, as I said, that so many of especially the graphics for those other, partially other content you see here, also come from my co-authors. So in this part is Vera Traub did a lot of the graphics you see here. So thanks a lot, Vera. She deserves a lot of credit for that. I just wanted to highlight that once more. So back to the relative greedy algorithm. So again, as I mentioned, this was introduced in the context of the Steiner tree problem by Zelikovsky. And the idea is simple, yet quite powerful, would say. Namely, what we're going to do is we're going to start with a very simple solution that is weak but heavily structured, and then we try to successively improve it. So it's just I explained right away in the context of weighted tab. So here we know we can find there's a two approximate uplink solution. So we compute that first. So remember there was this warm-up problem I gave where I said, okay, let's first once look at how one could obtain a two approximation for W tab. We said we can split each link into two uplinks, and if we have uplinks only, the problem actually is actually optimally you can solve it efficiently, because the constraint matrix of the natural RP is totally in a modeler. Let's just take that solution. So maybe this solution over here, where we split the links into uplinks. And what we're going to do actually is we want to have it even more structured. So we want to have a minimal solution of that type. This means I will shorten links, so replace a link by its shadow, by one of its shadows, if I can do so while still maintaining a solution. So here's such an example. So look at this green link here. Actually, I can replace it by the shorter link, by this shadow, and it's still a solution because by doing that replacement, there is the edge, this edge here I don't cover anymore by that green link, but it's already covered by the other green one. So that still remains a solution. When you do that, it's easy to see you actually obtain an uplink solution where every edge is covered by precisely one uplink. So there's no overlap anymore. Indeed, if you had an overlap between two uplinks, because they're both uplinks, this overlap, those links are, so this overlap will be such that one of the links can be shortened, when you think about it. It's not possible if there will be overlap in the middle, at least one of them has to overlap on an endpoint. Good. So we can find a two approximate uplink solution that's minimal. Minimal means that the paths of the uplinks, they're disjoint. Okay, so what's the plan? The plan is, let me start with a high-level plan, and I have to fill in some of the steps to be more precise. This is just formalizing this general idea of relative greedy. Oh, sorry for the scrolling, let's scroll back. So we initialize, so we start with this minimal two approximate uplink solution. And then we will successively replace some of those uplinks by other links. And those other links will be the links in F. At the beginning, there are none of them. It's an empty set, and I will then start increasing it, increasing F. I will decrease links in there. I will remove links from also, let me just highlight. So here we will we have always this uplink solution and then other links coming. So I will try to denote always by uppercase U the uplink solution, and I will use lowercase u for an uplink in that solution. So it's different to maybe the previous sections where I sometimes use lowercase u for a vertex. So here I try to be consistent and use it only. I mean, it was consistent beforehand too. I'm just not consistent between the two parts. I try to, in this part, consistently use u only for uplinks, not for vertices anymore. Okay, so the uplink solution so far, that's just a pure uplink solution, nothing else. And what we're going to do is we're going to do improving steps. So in one improving step, we want to select a well-chosen component. I have to be more clear in a moment how precisely we select that one. And so this could be so imagine that this is your uplink solution. So again, it's a minimal one. There's no overlap between the uplinks, and you might have some component C. Maybe this one here you want to add. So component is just a subset of links. And if I want to add that one, so I check which ones of the uplinks I can remove from my solution while maintaining a solution. And this set I denoted by drop U C. This means what can you drop from U when you add the component C. And those are just, by definition, the links in U that are covered by, so I only look at links in U that are covered by links in C. Right? It's precisely what you can drop. So in this example down here, let me just draw this. So I can drop this link, as this one here is covered, and I can drop that one here. So this would be the set drop, in this case, drop U of C. If the weight of what I can drop is larger than what I want to add, in that case, I do the kind of the swap. I add the component to my current solution. So again, everything I add freshly, I will add it to F, which is at the beginning empty. And what I drop, I just drop it from U. So I drop those links that are now covered from the set U, and I add the links in my component to the set F. And I keep going. I go back to the improving step. And as long as that works out, I keep going until I will have a component where where the replacement step does not improve anymore, in which case I just return the union of U and F. So the main variant, it's highlighted here, sorry, up here in the box, is that U union F will always be a solution. And you should, if you understand the procedure, the way I explained it now, this should be clear that maybe we only drop stuff if whatever is left is a solution. So that's the main variant. Of course, the big question is, how do you actually choose that component, right? How can you choose a component that makes progress? So you want to choose you're going to do this as follows. And that's a common strategy in relative greedy procedures. We actually first define a component class for certain types of components. A natural such class would be, look at components containing at most constantly many links, would be such a class. We would like to have two properties of the class. One is that we can efficiently find a component that minimizes this ratio of the cost that will be added by adding the components over what we win, what we can drop. So it's essentially bang per buck, what we're talking about here. And, or I guess to be precise, it's buck per bang because I'm minimizing, but okay, that kind of doesn't roll so nicely. But in any case, you got the message, you got the idea. So we want to minimize that over all components in K. So we want to have a component class that allows for minimizing here efficiently. And we would like to have so this, of course, it's not hard to find such component classes, but it has to be rich enough that we can make progress. So we want to make sure that whenever the current remaining uplinks are clearly more expensive than not, so when I write this much larger sign, I really just mean it's a 1 plus epsilon factor larger than op. So there's always a small epsilon only there, but it's just more convenient for me to write a much larger sign. So whenever you have whenever the weight of your remaining uplinks is way more expensive than op, then there should be a component in that component class that has a ratio below 1, which means we improve by doing this replacement step. Let's do a little warm-up that fails. Let's just think about what about choosing as a component class the constant size components that I mentioned beforehand. So that's actually if I think about the prior applications of relative greedy that I know about, actually by always taking, as far as I know, that class. So in Steiner tree, the class can be defined that way. People looked at Steiner components with the most constantly many terminals, which is also of that type. Here we could think about one with constantly many links, or maybe constantly many, something that covers constantly many leaves would be another option. It would run into the same issue. Let's just go for the simpler one. Let's look at components of a constant number of links. So here's an example of an example instance with the weights over here. Let me just be clear what those parameters are. So it's a general construction where I have one kind of big horizontal path, and there's some edges hanging off that path, and the number that is hanging off. So in this case, it's 3 to the left-hand side and 3 more to the right-hand side. So this total number is just D. I denote it by D. So D will be even in those constructions, and M is just a large constant. So, but keep in mind, D could be way larger than M. So D can depend on the instance, whereas M is a constant. Now let's just check what is the optimal uplink only solution. And what's an optimal solution here? They turn out to be unique. So so let's check. So optimal uplink solution. So you see the root is in the middle. An optimal, so the optimal uplink solution consists of the orange links and the brown ones. Let's see, this should roughly be okay, and the brown links. Whereas an optimal solution, the actual optimal solution, are all the blue links and the one green link you see on top. And you see this instance is now, okay, maybe let's first just talk about how expensive those solutions are before we start talking about how we could try to improve the uplink solution using the other links. So let's talk about cost. So if you only have uplinks, then we have d many of the orange ones and d many of the brown ones. So this will be d 2m plus 2. If you look at the optimal solution, you have d times 1, d of the blue ones each costing 1, and the green one, which costs d times m. So this is d m plus 1. So indeed, you have a factor 2 difference between the two solutions. That's of course if I want to show that the approach fails, I need to start with an uplink only solution that already is a factor 2 worse, because if that one is upfront already better than a factor of 2, smaller in terms of weight than a factor of 2 times opt and 2 times opt, then I already have a solution that beats factor 2. So this means here I would need to improve my uplink solution to be able to get a better into approximation. However, you see, if I want to replace some of the brown or orange links, I could replace orange by blue, but that doesn't really improve anything. It's a 1-against-1 trait. And of course, I could replace the weight of blue from 1. I could replace 1 by 1 plus epsilon if I want to make sure there are no ties. And for the brown ones, to replace the brown one, I need the green one on top together with the blue one. But it turns out the green one is super expensive. So such a replacement step really only makes sense if you have enough blue ones together with the green one that you can use to kick out a lot of the brown and orange ones. And if I choose that constant m large enough, you actually need to cover about half of those things that are hanging off. So like about d half of those brown links have to be covered. This means you need a super constant size component to even see anything that could potentially improve your solution. So constant size link sets is not going to work out. And I guess also it's one of the main reasons I assume why previously people didn't make improvements on TAB with relative greedy approaches, except for a special case. Is a very nice paper by Cohn and Newtoft that also inspired significantly our approach, but their approach only works for trees with a bounded diameter. It also uses a relative greedy approach. I will get back to the parallels between what I'm showing to you here and what they did later on, when it's easier to explain. Okay, so that's a bad example. So what we're actually going to do is we're going to look at another component class, namely constant thin components. So what is the thinness of a component? A component is, a component is just always a subset of the links, right? So there's nothing, I just call it a component, but you can think of it as a subset of links. And such a component is k thin if for any vertex there are at most k paths of the component that go over the vertex. Let's look at this example. So these 3 links together is a component that's too thin. It's too thin because if I look at any vertex, let's say this vertex here we have 2 paths of the links. If this is L1, so it would be the path of L1. 2 of those paths go over V, but no more than 2. And that's true for each one of the vertices. That's why I call the component too thin. So, by the way, if you go back to that example, you see that the optimal solution is actually also too thin, because you have the vertices up here. If you look at the green and the blue links, the vertices up here are in 2 paths, in the green path and one of the blue paths, and that's it. The vertices down here are only one of the paths, and the one corresponding to the blue link incident with them. So therefore, here indeed we have the optimal solution is too thin, so that one could actually even be part of our component. So we could right away just take the optimal solution and replace everything we have so far. So it's a good sanity check. So the bad example is gone with that definition. So now what we have to discuss is, and what I will discuss in the following, is that it's 2 things. Actually, just these 2 properties are that we actually achieve our goal. So we can actually find efficiently a minimizer of a component minimizing that ratio among all components that are constant thin. So it's a K or some class of constants in components. I have to fix a constant. It will be 1 over epsilon. And it turns out we can do that through a dynamic program. The second thing I have to show is that we can actually make progress if our uplinks, current uplinks in our solution, are way more expensive than opt, then there exists a component in our class with which we can make progress. And this will be shown through that decomposition theorem. So let's go step by step. Let me start with the dynamic program. And again, I just sketch it because as I explained already last time, it would be quite cumbersome to give all the details, but I hope the sketch is good enough that you can fill in the gaps if you want to. And as always, I mean, feel free to ask questions if anything is not clear. So what we're going to do, so we should minimize that ratio. Let's first do a standard transformation. So instead of minimizing the ratio itself, we're going to minimize actually the numerator minus lambda, the denominator, for some coefficient, for some lambda, for some fixed lambda. I show that you can do that. So if I can show you that you can do that, then I claim you can also find a minimizer here, or at least approximately, because if I could set lambda, if I knew what the minimizing ratio is, I could use that one as lambda, and then any minimizer here, it's non-empty, would be precisely a minimizer of that ratio. So what I could do now is I could just try to, so essentially to find the largest lambda here, such that the minimizer we have here is, I guess, larger or equal than 0. I hope I set this right. Let me just check. Yeah, that makes sense. So the so actually I could do some binary search over lambda to get the right one. But it turns out actually the procedure I'm showing you will be what is called a fully combinatorial procedure. So in that case, one can also use another standard, nowadays standard technique, namely the parametric search by Megiddo, which will give you the correct lambda in polynomial time. But you can think of the we guess the lambda through binary search. Again, in any case, it will lose a 1 plus epsilon factor somewhere, so we can also we're fine not getting the precise lambda here. Okay, so let's see how we're gonna minimize that expression. So I claim we can minimize that efficiently. So we consider constants in components. Let me just name what the constant is. Let's say the constant is k. Consider k in components. And so what we're going to do is, I would like to, so dynamic programs, so I will not build solutions bottom up. I will again give you the how a table entry looks like for the dynamic programs. What kind of things am I saving? So I will have a root somewhere, an arbitrary root. Let's pick the root here. And now for any subtree, so subtree is defined by a vertex. Let's call it B in this case, and all the vertices that are on the non-root side of V. I would like to understand, first build solutions using links that cover at least something in that subtree. And so what do I have to, so I want to find the best solution in there. Now the question is, what do I have to save that I'm able to then complete the solution when I try to propagate and look at larger subtrees. So as usual, dynamic programs are mostly about finding a good fingerprint, finding a good way to understand, decomposing a problem into a smaller part and trying to understand what exactly do you need to know about the solution in the smaller part to be able to complete it to the bigger part, to a bigger part. And so let me be formal about this, a bit more formal about this, so that the dynamic programming table entry we are saving, we have one for each triple. So what's a triple? So the first thing is what I already said. We want to have solution for each subtree. And when I say that a solution for a subtree, I'm looking at links, only at links that cover at least one of the edges in that subtree. The second thing is I also want to know sort of links that are fully inside that subtree and some that actually also go outside. but there are at most k that will go outside, because any link that covers something inside and outside must go over V. And we said we're only looking at k-thin components, so there can be at most k such links. So I will also have, I've actually look at any subset of at most k links going over the vertex. There's one more thing I need to save, I need to keep track of in my table entry. So now, of course, what I would like to do is I would say, oh, among all those solutions that have some links inside here and at most k links that go out, I want to actually find the one that minimizes that expression here I want to minimize. But there's still one dependence between the inside and outside problem that I didn't capture. Namely, there can be up to one uplink that has partially contained some edges inside and some outside. Let me just draw an example. I think it's much clearer if I leave an example. Look at this uplink here. It has to be an uplink, so the other endpoint needs to be between one endpoint and the path to the root. Let's call uplink U. So that's P of U, the one I'm drawing here. And the thing is that, I mean, whether or not I can cover this uplink later depends on whether I already covered these two edges down here, right? So I need to, let me just highlight them. So the light blue ones. So I will actually have also a binary flag that tells me whether I covered this part or not. Whether the parts of PU within the subtree below the vertex V is covered. So let me be clear, or just at least make the link. There will be the part of PU within the subtree below V that's precisely this light blue part I showed here. So for each of those triples, I want to save a solution that the one that minimizes that expression here. And one can observe that if I can do that, I mean, that one can do that and actually then propagate solutions from smaller to bigger subtrees. So you start with subtrees consisting only of one vertex away from a leaf, and then you can go up and combine solutions.
Just to check, Rico, the two edges closest to the root there are not part of PU, are they? Right.
Oh, thank you. Thanks, Neil. That was wrong. This one here is not part of PU. And this one also not, it's not part of PU. Yeah, thanks a lot. Yeah, perfect. Yes.
Rico, when you say binary flag indicating whether part of PU within subtree subtree below V is covered, it's covered by the current uplink solution U, right?
So what I mean with that is, so I'm looking at solutions consisting of links. Let's look at all the links that cover at least one of the edges of this subtree here. So I only look at those links. I will not allow myself right now to pick links that are outside. Now among those solutions you can pick with those links, I will look at solutions that contain a specific set of k-links that go over V. And now I will save two solutions, one for requiring that you cover that those links I pick, those are not the uplinks I pick, but actual links of the problem instance, that they cover the light blue parts, and another solution where they don't need to cover it. And for each of these two solutions, I want to find the one that minimizes this expression. So I want to find the cheapest one, the one that has the cheapest value up here, the lowest value up here, and covers light blue, and the one that has the lowest value up here and does not cover light blue. Because later on, if I know I cover light blue, later on if I cover the remaining part of the path here, I can actually then make sure that I know that it's not part of drop, because now it can drop U as well once I cover the whole path. And this I have to keep track of, because otherwise I'm not sure whether later on U may become part of drop U from the solution I have or not. Because if I don't know whether I covered this part here, I can't tell later on.
I see. So the binary flag indicates that so in the subproblem that I solve, I have to, if the flag is set to 1, then I have to cover, and if it is set to 0, then I don't have to worry about that. Yeah.
Exactly. Yeah, you got it. Yes, that's it. Yeah. Essentially, I'm saving two solutions for two different scenarios, right? That are at that moment somewhat not comparable, but it's precisely what I do. Yeah. And later on, I will then figure out which one was the better one when I keep propagating them. Yeah. Thanks for the question, Daniel.
Yeah. So I think I missed it. How do you determine PU, or that blue part? I didn't get how it was determined.
Very good. So what you're okay? So good point. So what is given? What do we try to do? So you're given. Let's assume I'm at the very first step of my relative greedy procedure. So I'm given an uplink only solution U, and this I construct explicitly through that link splitting procedure. I get a two approximate uplink only solution, and I shorten it to make sure it's not overlapping. Right now, I would like to understand: is there a good way to add a certain link set of components in a way that if I look at how much I pay for adding the component versus what I win by dropping links from you that are now covered? So what is what would be a good component for that? So for that, assume I have the right factor lambda, the one that corresponds to the best ratio, and then U is actually given. I see the uplinks, right? So I can now figure out when I look at a bunch of links I want to add in a component, I can compute which uplinks can be dropped from my current uplink solution. And this is
but inside that component only, or
like, say it again, Daniel?
So if you have a bunch of links that touch the component that you're focusing in on now, that maybe you want to use, and now are you looking at like the uplinks that they could potentially maybe cover in the future?
A good point. I'm doing that. I should highlight one more point that may clarify this confusion potentially. So keep in mind the uplinks, they cover disjoint parts. So the PUs are disjoint. This means there is only one uplink, at most one uplink, that has a PU that covers part inside the subtree and this edge outside of the subtree. Because there are no two uplinks that can cover this edge here, because the uplink solution covers disjoint parts. And therefore, now back to what you said beforehand. So essentially, this is just one uplink that could potentially be covered later on and has to be covered partially already in the subtree. That's this one uplink U. And for that one, I want to know with what I covered in here, whether I did cover the part that lies within the subtree of the uplink or not. Because this tells me whether if I cover the rest later on, whether I can then drop the link or not.
Right, but so just if that edge going from V up towards the root.
Exactly, this edge here, let me just name it. This edge.
Yeah, so that edge has to be covered by somebody.
Exactly.
Right? Okay, so there is always some uplink that covers that edge, and it's that uplink.
I mean, it could be that it's an uplink like this, right?
Oh, and it just stops.
Yeah,
it doesn't go into.
In which case, there's no dependence between the inner and the outer part, because that uplink has nothing to do with what happens inside. In that case, I don't need the binary flag because yeah. But otherwise, you're right. It's just one uplink that captures something inside and something outside that subtree. Yeah.
I see. Okay, thank you.
Yeah. No, thanks for the question. I'm very happy we can clarify those questions now, because it's a crucial procedure. I will use it again later on, and I know I'm a bit hand waved in terms of the way I explain it here. Perfect.
So, Rico, the third bullet. So you only care about one path PU, and that's the key here, right? So here you're really exploiting that the uplink solution is disjoint.
Exactly. That's a good point. I should highlight that. You're right. I mean, because the uplink solution is disjoint, then there's only at most one link U that captures that will cover something inside the subtree, something outside. Therefore, I just need one binary flag to understand the interaction between inside and outside, namely for that uplink. Otherwise, if there were like more, I would need one for each uplink that covers something inside and something outside. And then, of course, suddenly the number of table entries would become exponential. But the way I define it, number of table entries are polynomial, right? And here I crucially exploit that there is at most one uplink that has this property covering something inside, something outside.
And there might be uplinks covering E because it's been switched to some non-uplink already, right? Like if it's been removed from you.
Yeah, exactly. It could be exactly. It could be that indeed. So we have them. So now we have with iterations in the relative greedy procedure. It could be that already some prior iterations covered some of those uplinks, and maybe there's just no uplink left that covers E because E gets covered by something in F. No, you're fully correct, Neil. Good point. I kind of so far explained it as the first iteration, but the same reasoning applies later on. Important is simply that those uplinks, they cover disjoint parts. You never have more than one link with that property. Yeah, thanks for that question. Perfect.
Can I ask just one more clarification? Yes, sorry. Just the light blue part in your case consists of two links, but you only want to remember whether you covered both of them or whether, like, what if you might have a solution inside the subtree that only covers one of these two edges?
Yeah, if it covers one of the two edges, then I know the other one will is uncovered, so I will never drop that link U later on, because I know there's one link that remains uncovered.
Okay, so it will be a 0 in your binary flag.
Yes, exactly. This would be a 0 in the binary flag. I would not cover it. I know I can never cover it later on, because I guess the K links that go over V, I will not take any other links that will go over V later on. So links that kind of go back in.
I see.
So that one is, yeah, that's over. We can't cover U anymore. So the flag will be 0. Yeah, you're fully correct.
Okay, great. Thank you.
Yeah, thank you. Perfect.
One more question to tag on here. So this subproblem 1 on your left side, to write this dynamic program and solve it, you're relying on the uplink solution already being well structured. If
yes.
the solution is not well structured, can you still solve that subproblem 1, or?
Yeah, that's a good question. So I don't know. So if it's not structured, at least not that way. Now it kind of depends. I think you need some kind of. I mean, it's a bit of an interesting question, right? In the sense that, I mean, if you have an uplink solution, it's not structured, right? Not structured means not minimal. Then you have edges that are double covered. So then you could just as well first simplify it and structure it. It's kind of strange because you don't need a link. I mean, you don't need to double cover edges. So I don't see a reason why you would not first simplify it in that case, right? But if you have maybe a different type of solution than an uplink solution, you could also think about maybe starting with a better solution than an uplink only solution, and you could still hope to be able to minimize the ratio. So now it depends what kind of solution you start with, and I don't know of a good class except for this very structured uplink solution to start with for the time being. But it's a good. I mean, actually, I'll give. I may make things a bit more precise. I'll show later on in the local search part a way to reduce a more general solution to that case here. And so it will partially maybe give you an answer to your question, Kartik. Yeah.
Thank you.
Yeah, thanks. Yeah. Thanks for all the questions. So that's the DP. So we can minimize such expressions for any fixed lambda. And now let me talk about the decomposition theorem. So what does it say? So what we show is that for any constant epsilon and any uplink solution that is minimal, so the path of disjoint, there exists a partition of opt. But let me be precise. I mean, I write opt here, but this could be, of course, could be any feasible solution. We just apply it here in the context of opt. So I just write opt because it gives you the link of how we think about it in terms of improving things, but it's not necessary for the statement itself. So there's a partition of it into constant thin components. So the thinness is 1 over epsilon. Such that if you look at those components of opt and you look at what you can drop if you at any of those components, just sum all of them together, then it turns out you can drop almost all of you up to a 1 minus epsilon factor in terms of the weight. So essentially it localizes the improvement step. So of course, let's just do a little thought experiment. I have an uplink only solution. Of course, the dream would be that I can do what we had in this bad example for constant size components, because that bad example, the optimal solution is too thin. So I could just take the whole optimal solution and replace all of my uplinks against the optimal solution, and would experience a huge improvement. But what this statement shows, no matter how the optimal solution looks like, so even if it's highly non-thin, you can split it into many thin parts. And if you look at what you gain by just adding one of them over all of them, seen over all of them, then you can almost remove all of the uplinks up to an epsilon fraction. So, so that's it localizes the improvement step. Let's just see. Was there a question? Maybe I just missed.
Yeah, I just want to ask something very quick.
Please.
So your uplink only solution is, in your language, a one thin solution.
That's true.
So like the initial step, I mean, could you think of it as using your DP to find a one thin solution? Like the best sort of one thin solution among the links. Yeah. Or like you could even do the best two thin solution or three thin solution for the starting solution to your procedure.
That's a good point. I think you can do this with a DP. Find the best 2 or 3 thin solution. I think so. Yeah.
Yeah. Okay.
That's a good point. Yeah, I think you could do that. It would not immediately lead to improvement in the factor the way I do things later, but indeed this is a possibility. So kind of thinness is kind of I think this highlights one important aspect that you just identified here, Daniel. Namely, thinness is really nice for dynamic programs because there's only a limited number of links that interacts between what you cover so far and what you want to cover later on. Good point.
But I thought thinness is the number of related to the number of links that go through a node. So the end, like for uplinks, why it is one thin? Can't you have a star with all uplinks and the center will be inside a lot of this path?
Oh, good point there, Lauren. Sorry, I think I messed up beforehand. Yeah, but you're right. No, uplinks. Okay. No, indeed. This is the way I define thinness. This would I think I could define it slightly differently, allowing for such interactions, right? Because to build a dynamic program the way I did it here, I'm okay if links, if many end at the vertex B. The only thing I don't want is that you cover stuff inside and outside. So I think there's a more general notion that would, where this would be, I mean, I could just talk about thinness in terms of number of links that contain a vertex in the interior. And I think things which will still work out that I do here, because the dynamic program doesn't need to look at links that contain a vertex as one of the endpoints. But you're fully correct. The way I define it, this would not be one thing, but there's another way to define it that would lead to one thing. So, no, thanks for that comment.
Yeah. Okay.
Perfect. So let's just talk about why this decomposition theorem leads to what we want to have. So let me just recall the second step. So one was, I can optimize that ratio to get the best component with respect to that ratio, the ratio here, minimizing the ratio. And the other one, I just recall it here, we wanted to have the property that if the number of uplinks left is expensive compared to opt, then there is a component that's improving. Right? So let's assume that's the case. Let's assume that the uplinks we have are expensive compared to opt. So at the beginning, that we can assume that's true because at the beginning we started at 2 approximation. And we can assume it's essentially a 2 approximation because if at the start you're already better than 2, then we already improved the factor 2. So let's assume that at the beginning we're really twice opt in terms of weight. And so in that case, what we have is if you look at this sum and what we can drop, then by, let me just make the link, then by the decomposition theorem, so this would be this inequality here, it's just the one up here. That's at least as large as 1 minus epsilon times the whole weight of the uplinks. And now I use the property we have here that the total uplink weight is significantly larger than opt. So again, significantly larger essentially means by a factor of 1 plus epsilon, or here 1 plus 2 epsilon to be on the safe side. So it's not, the gap doesn't need to be big. And last but not least, remember that we partitioned, so up here we partitioned opt into those components. So that's the same as the sum of the cost of the components. Right? But if you look at that, then by an averaging argument, there must be at least one component for which the left-hand side is larger than the right-hand side. And that's precisely what I want. Then it gets a ratio below 1. So maybe we can think of it that way. Or maybe, okay, I think this is maybe, let's leave it the way I wrote it. So essentially it shows that, and also maybe one more thing I want to mention is that, so at the beginning, I mean, this inequality is very loose because the uplink solution will essentially be about 2 opt. This means that at the very beginning, we will actually be able to find a component that has a certain weight that we want to add, and we will win just about twice that weight in terms of obliques, at least twice that weight. So at the beginning, you have a factor 2 improvement on the exchanges. But later on, the obliques will have fewer and fewer obliques, and so the improvement will decrease. And as soon as the weight of our remaining obliques is in the order of opts, the reasoning doesn't give any, doesn't guarantee any progress anymore, and the procedure may stop. Or may be lucky and find another component, but there's no guarantee that we get through the decomposition theorem at that moment. Now, let me try to see how am I doing with time. Let me try to give you an explanation or a more formal reasoning. Now, why do we get this approximation factor of 1 plus natural logarithm of 2? And so it's a kind of a more of a proof that we can explain things nicely on a diagram. It should be fully contain all the ingredients you need to know. And it's a bit easier maybe than the proofs you will see in maybe in the paper or in other papers on the relative degree. At least I hope you feel it's easier. I do. At least it helps me to remember how things work. So let's look at the solutions. And so I'll have two axes here, one capturing the weight of our current set U of the remaining obliques, and one capturing the weight of our set F. So at the very beginning, now let me try to make sure I get it roughly right. So at the very beginning, we have the set U0, and let's say the weight is up here, and it's no more than twice the weight of opt. Let's say it's about twice opt. This means opt would be roughly here. So what does the procedure do? So the procedure starts with U0 being the initial solution. And then we start finding components and dropping stuff from U. So the next U will be U1, and we'll have strictly fewer elements in there. And then we'll have U2 and so on and so forth. And after a certain number of iterations, let's say Q, let's say the procedure stops after Q iterations. On the other hand, the set F at the beginning, it's the empty set, it's F0. And that one is going to grow, right? We're going to add components and so on and so forth. And the last one will then be FQ. So the return solution will be UQ union FQ. Remember, the algorithm, it just replaces things and returns the union of whatever is left from the uplinks and together with the components we contracted. So at the beginning, so we are up here. Actually, this point, strictly speaking, is the point where we have the weight of F0, which is 0 because we don't have any actors in F0 at the beginning, and the weight of U0. So what happens at the very first step? So the decomposition theorem you see here on the left-hand side, it says that if you could contract, if you look at the components coming from opt, if you could contract all of them, you would win all of the obliques you still have in your solution. Okay, I was lying. It's not all of them. It's the 1 minus epsilon times the weight of them. But let's forget about the epsilon for the time being. It doesn't really have a big impact. So you essentially win all of the obliques in your current solution. So what does it mean in terms of how fast we will make progress? It means, let me add this here. So this will be the weight of opt again. It means that we will improve roughly with at least that slope, or at least we precisely say at most that slope, because going down is good for us, right? We want to decrease a lot in terms of what we pay in terms of obliques, and then only have to pay a little bit extra in terms of what we added in other links. So the decomposition theorem tells you that after one iteration, you will have a solution U1, I mean F1, U1 that should be on or below that line, up to a 1 minus epsilon factor. Again, let's forget about the epsilon factor. So what you will get is, let me just pick a point. Let's say you get this one. So that would be the weight of F1 and the weight of U1. Of course, the slope here should be strictly below -1. So because the -1 is break even, you will just add as much weight as you remove, so there's nothing happening. The algorithm wouldn't make an improving step in that case. We'll only make an improving step if you have a slope below 1. Now let's continue. So what happens now is that, so what is now the slope, the guarantee we get through the decomposition theorem? So here we now got a little bit away from the x-axis by WF1. So there will be a point. Let me just write down the green point here. Let me just reorganize things a little bit. So this is the weight of opt plus the weight of F1. So now I know that whatever is left in terms of uplink weight, so left in terms of uplink weight is this. I can win all of that if I add the full opt, all of the opt components. This means this time I will have a slope that's at least as good as that one here. So maybe I will end up say somewhere here. So that would be the weight of F2 and the weight of U2. Perfect. Let me do one more, and then I will try to conclude on the whole procedure. So just a rough guess. So this would be, let me change the color first before we start confusing things. So this one would be the weight of opt plus weight of F2. So here, this time we will have, we can win whatever is left in terms of uplink costs. So in this case, that would be all that. If you add all of opt, so this time the decomposition theorem guarantees that slope. Okay, let me just add the point here. This may be the third step.
Rico?
Please.
I don't think I get why we're adding the weight of the F to opt.
Mm-hmm. You mean down here?
Yeah.
Yeah. So the thing is that, so right, let's look at the first step. The first step, after first step, you have a solution F1. Oh, this is not a U2, this is a U1. I just messed this up. So you have a solution F1, U1. So the union of F1 and U1, and that's an actual solution.
Yeah.
And you know that if you now add the whole of opt to that solution, then you could win all the uplinks. The problem is that
what does that mean, win all the uplinks?
All the means all the remaining ones, the uplinks in U, the U1 links, the links in U1. So you don't have all the uplinks of that you had at the beginning anymore. You have only a subset of them because you dropped some of them from U0 to U1. The problem is with that decomposition theorem, it only it works for any subset of uplinks that are disjoint. At the beginning, this will be a full solution, but later on, it's not a full solution anymore. And this actually weakens the decomposition theorem because it tells you that you can actually drop all the weight that is left on the uplinks that you still have by adding all the components of opt. But it doesn't tell you anything about the other links that you added already, the links in F. So this means when you are at the solution F1, U1, then the decomposition theorem only applies, we apply it only to U1, to the links, to the uplinks that are left. This means that what you can gain is this orange line here, in terms of if you only analyze uplinks. That's what the relative greedy does. It only analyzes the easy part of the solution, the uplink part. But the decomposition theorem says, oh, you can win it by just a partition of the whole of opt. And if you contract, let's say, all of them, then you can drop essentially everything of the uplinks. But you always need to add all of opt to drop all of the uplinks according to the decomposition theorem. And that's why I have to go from this line here, where I'm now, opt to the right, which brings me here. And this means that if I could add all of opt, I would end up here on the green point. And I would win all of the uplinks. I would get down to no uplinks and all of opt. So the decomposition theorem says that in average, you will actually be at least as good as that line. It's one way to think about it.
I see. And I guess I misunderstood that the shifting to the right makes things harder for you.
Yes, exactly. It gets harder. So you see the slope, the gray slope, it gets weaker, right? It is. I mean, negative is good. I want to have a negative slope because, I mean, the actual solution value is not the y value, the y-axis here. The solution value is the sum of the two coordinates, right? Because I always have u and f. So this means that I do improve as long as the slope is strictly below -1, because then I exchange something bigger against something smaller. And you see at the beginning, it's actually about -2, and then it now slowly gets weaker and weaker. And at some point, they may not make any progress anymore. Does it make sense, Daniel, the way I explained it?
Yeah.
Perfect. I got one more question on the chat. Let me just mention that one and answer it. So the question is, do I understand correctly that it's impossible to get that the uplinks are below opt, that the weight of the uplinks are below opt? So actually, it is possible here too. I will get it once I just go below opt, but the comment is a good one in the sense that once I'm below opt, the decomposition theorem gives me no guarantee in terms of improvement, because now it just would tell me if I invest whole of opt, I can win whatever uplink cost is left, but the uplink cost is less than opt, so it means I will win less than what I have to pay if I just use the decomposition theorem. So indeed, the theorem applies as long as I'm above this horizontal line, W opt. Later, of course, it may be lucky. It's always possible that the algorithm keeps going and finds more components that work out, but the decomposition theorem doesn't guarantee that they exist. So let's just assume it's not going to happen. But thanks for that comment. Very good point. Very good. So let's just look at those steps. In this case, the procedure may continue, but as I said, we don't know whether it does. Maybe it will continue and will end up at some point maybe here, maybe even on the other side on the gray line, potentially. This may then be the f of the w of fq, w of uq. This could potentially be the last one. But again, there's no guarantee that I make progress below w of opt. So what I will do actually is, so the weight is, weight, the return solution has, as we said, has a weight, just the weight of uq plus the weight of fq. But when you think about it, that's at least, and I'll need a good color. I used almost all my colors here. I will just reuse one. Let's go for blue. Blue should be fine. Let's look at that. At that point here on the black line. This should have been a horizontal line. And let's call this T0. So you should agree, or I hope we can agree, that the value you obtain is at least as good as this blue point, as the value of that blue point. Why that? Because it lies on the black line, and the black line always has a slope below -1, so it keeps improving. So we only do improving steps, so you'll actually get something where the sum of these two values here, where the sum of f of the weight of fq and weight of uq is no bigger than for the blue point here. So what I will do is I will actually show that the blue point is already good enough. It gives you that factor of 1 plus natural logarithm of 2. And if I can show that, then you have the factor for the final solution. Of course, I mean, I can't figure out when I'm there during the algorithm because I don't know the weight of opt. I'll just keep going as long as I improve, and then know I will cross that point at some point. And I'm not sure the way I like to analyze this procedure. So this curve, let's call it g of t, the curve, the black curve. Let's try to analyze it. So we have a differential inequality. So if you look at the slope, I put a minus here because the slope is always negative. So if you have minus the slope, that just tells you what is the improvement. So we said let's just do the reasoning formulae I did beforehand. I said, you can win all of g of t at any moment t by investing the whole weight of opt. So the slope will be always as good as g of t divided by the weight of opt. On this part, at least on the part until t0, so the way we discussed it, I know we can make progress. That will be that's precisely the gray lines. I just formalized the gray lines. That's all I did. As soon as you agree with that, we're actually done. I just resolved that inequality. So let me just try to do it the way I learned it, I guess, a long time ago. So let's integrate minus, so it would be 1 over gt dgt. That should be larger or equal than the integral of 1 over w opt of dt. And let's just agree on integration bound. So I'll integrate from 0 to t0. So from 0 to t0. This will correspond to starting at the weight of u0 and going down to the weight of opt. So weight of u0 up to weight of opt. So you get this inequality by just resolving that inequality up here. Now this will lead to minus, so the minus I can pull in the logarithm of, let's see, so it will be natural logarithm of GT. I have to plug in opt in U0, it will be W U0 divided by W of opt. So the minus just change the numerator and denominator. And on the other side, let me pull the W of opt to this side here. So we will get that. Just resolving that inequality. And now I can use it over here. So let me be clear. So the solution we obtain here, I can replace T0 by that expression. And what I get is I get W of opt, the weight of opt, times 1. So the 1 comes from this term, plus the natural logarithm of the weight of U0 divided by the weight of opt. And so keep in mind, this is at most a factor of 2, because it started with a 2 approximation. So I got a 1 plus ln2 approximation. And you'll see how the different quantities play into that approximation factor. So if you happen to start an Abling solution that's better than a 2 approximation, you will just get, let's say it's an alpha approximation, you will just get 1 plus the natural logarithm of alpha instead of 2. Right? So that's one way to show that factor. Of course, you can also discretize things and analyze separate steps. That's what we do in the paper. But to me, at least, it helps to think of it that way, because I kind of nicely see it helps me to understand where we improve and we don't improve anymore, and where the factor comes from. It comes from that differential inequality. Well, let's talk a bit about the decomposition theorem. So I have like a little bit of time left, not that much. So I'll actually just tell the main parts of the theorem without going into the proofs. So this just I just recall the theorem up here. It's the same one you've seen already, I think twice. And the proof strategy is we will show that the following holds. So there actually exists a set of links, of uplinks, that if you remove them, then you can cover with, if you can decompose opt into components that cover all of the rest. The drop covers all of the rest. Let me just give you the example. It's probably much easier in the statement up there. So look at this example here. You see an opt solution and an uplink only solution, the ones with the blue one. It's a disjoint uplink solution. So let's assume we want to cover, we want to work with 2 thin sets. So opt right now is not 2 thin, it's 3 thin, right? Because there's vertex here, for example, is contained in all of the path. However, what I now can do is if I remove that link here, and just decide not to cover that uplink, then I can split, so I can partition the optimal solution in 2 components, the light green one and the dark green one, such that each of the other uplinks is covered by at least one of these 2 components. So that one here is covered by the light green component, and I guess all the other ones are covered by the dark green component. So this proves, if I can show that. So what you have to show precisely, you have to show you can remove an epsilon fraction in terms of weight of the uplinks, and then you can cover the whole, you can find a partition that covers the whole rest. And when I say covers the rest, I mean that for each other uplink, you can find one part of the partition covering it. Again, it localizes things. You don't have to look at the whole of opt to cover the other links, but one of the parts is enough to cover it. There will always exist one. So it's the main difference. That's the localization property of that decomposition theorem. That's what we're going to show. So what is the proof strategy? The strategy to prove that, actually the outline to prove that proof strategy is, so what we do is, and here we follow at the beginning an approach by Cohen and Newtoff. Namely, first we look at each uplink separately, and we will define a subset of the uplinks that will cover that uplink. So here's could be these 3 red links, they cover the uplink here. And here there may be a lot of overlap. It could be that I use the same uplink multiple times. Once is going to be used for that uplink here. Maybe there's another uplink that also uses that link here partially to be covered. But I just make sure for each uplink I have a set of uplinks that cover it. And then we will choose. So maybe let's first just look at how things will look like once after we did that. So I'd like to look and so the second type of graph, and this is a graph where the vertices correspond to the links of opt here. So just to make sure we don't start confusing things too much between the original graph and this link graph, I will always draw the vertices here as hollow ones, so with a wide interior, and I'll actually call them from now on nodes if I don't forget about it. So when you see hollow vertices is a link graph. Every vertex here, every node here, sorry, start doing it. Every node here is a link of opt. And so every set you see here corresponds to the links of opt we need to cover one of the uplinks. So let me let's copy the uplink U1, for example. U1, and this may be FU1. These three uplinks are the ones we needed to cover the uplink U1. And this would correspond to that set here, or say U1 is here, sorry, to that red set here. So the three links you see here are the three nodes over here. And this set just tells you, if you have a set for each uplink, if you want to cover that uplink, you can cover it by having these three opt links together in the same component, right? So now, of course, what they could do is ideally, I could not just look at this hypergraph and just look at its connected components. And if I look at each connected component and split opt into those connected components, I have the property that each uplink is covered by one of those connected components, right? But clearly it could be that it's just one big connected component, and maybe I make no progress. So what we're going to do is we want to now choose a set. You said we don't cover all of the uplinks, but only a subset. So we'll remove some of those sets here. Some of this just correspond to the uplinks we want to cover. So I will remove some of the uplink sets here, such that we get, of course, more components, and hopefully k-thin, constant thin components. And those will be the partition of opt at the end. Question is, of course, how to do it, right? How can we remove them in a way that everything works out? And that's the challenge. And so what we're going to do is, and now I will keep it short, I guess. So we can show, what one can do is one can represent these dependencies between the different links that are represented as nodes that are needed to cover one uplink. We can represent this in terms of a directed graph. And again, this idea goes back to Cohen and Muthoff, and I think so it's an extremely nice idea. Namely, if you look at an uplink, let's look again at this uplink here to be covered with the three opt links you see down here. Then essentially, if there's a minimal set covering it, then each of those uplinks covers a part that's not covered by any other link. So for example, the link L3 here covers this part. Let me use a different color. Covers this part here of PU that is not covered by the second link or the first one. The second one covers this part that's not covered by any of the other two links, and the first one covers that part. And so there's a natural ordering, right? One covers the bottom part, and at some point some other link had to take over to cover more of the uplink U, and some other one had to take over. And this ordering, we create a directed graph on the nodes here, on the link graph, that just represents this ordering. What one can show is, if you choose those FUs minimal, and now I skip all the properties, one can show that oh, maybe let me go back and just say one more thing before I keep going. So we do this for each uplink. We now have such a dependence, and now we put all of those arcs together. Then we have a graph on the nodes, on the links of opt, with the dependencies indicated by those arcs here. And if you do that, it turns out that the graph is a branching, or if you, let's simplify things and assume that if you go, let me scroll once more back and apologize for scrolling. If that graph here is connected, if it's not connected, we can anyway independently work on each connected component. But if it's connected, it turns out that that graph you obtained will actually be an arborescence. That's a key property, and it follows. It's actually quite easy to show that it's an arborescence. I will just show that because I think it's nice to see that. Why is it an arborescence? Because let's just look at one opt link. Let me just draw part of the graph. So again, these are filled nodes. That's the original graph, not the link graph. And let's look at one of the. Let me just draw one opt link. Let's say this link here. And let's just try to understand what could be a predecessor of that link in the dependency graph. So predecessor means, we'll scroll once more back, means that it's part of one of those FUs. It's maybe the link L2 here, and then there's a link above it, an L1, right? That covers the remaining part of some or more of the uplink that is already partially covered by this link. But it's just one uplink that that can have the property that L2 will be they'll have a predecessor in that corresponding set FU, namely it will be the one, if L2 covers part of an uplink but not everything, it must be an uplink that covers the edge E. If the uplink finishes before that, then it's fully covered by L2. There's no more dependence that comes from that uplink. So it must be some uplink that covers E. It could be that one here. Maybe it goes even further down. Who knows? Maybe it looks like that. So there's only one uplink for which L2 may have a predecessor. And for each uplink, there's just a unique path here, just one path we add. So it has a single predecessor. And that's why it's a branching or an arborescence. It's a quick explanation, but it gives you an idea of why this happens. Now I'll shortcut a bit. So that one can show them, we need one more property. And I'll just explain that. So it turns out that just choosing minimal link sets covering uplinks is not enough. You have to make a better choice. And that's also one point where we clearly deviate from the Cohen and Newtov approach and also get way more properties later on. Namely, among all possibilities to cover U with optlinks, we will actually try to find one. Let me just give you one of them. Let's choose one that will help me later on. Let's pick this one here. That's one way to cover all of U with optlinks. So the red is opt. So if you look at that way of covering U, I will look at the apex. So if you look at for each of those links is an apex. So this one here, the apex is this vertex. It's just the vertex closest to the root. Let me just maybe be explicit. If this is L1, this would be the apex of L1. I will choose one solution, one way to cover U, to cover P of U. So let me just add that here, such that the largest apex is as low as possible. So this would be one way to do it. It's a minimal way to cover the path with the largest apex as low as possible. So let me just give another way to do it that I don't want to do. Another one would be I pick this link, then that one, and then this one here. This one here would have the largest apex up here. So I will not pick this one here, will pick one with the apex as low as possible. And it turns out what you can show is, you can show a couple of nice things. One thing, so this doesn't yet need the property, but it comes soon. One thing is that for each of the, if you look at a single FU, so the links, the optlinks, you need to cover one of those paths, they'll actually always be too thin. And we can prove a stronger property. So I'll skip the proofs. Maybe that's the most important one. I want to focus on that one now. Namely, we can show even something stronger. It turns out that if you look at the vertex in the original graph, and let's look at all the links that cover that vertex, so that such a vertex lies on the path. So this VL1 is the vertices on PL1. Then it turns out that those links, they will form a path in this, or they have to lie on a path in this graph here. So if you have a vertex that's covered by many links, those links will lie on one path here. This gives you a guarantee on the thinness, because if you look at a path, we said that each of the colored parts, so each color corresponds to one half of U, each of them is too thin. If you have 10 colors on one path, then you have to guarantee that it's a 20 thin set, the links on that path, because it's a union of 10 too thin sets. And finally, what we will do, we just want to give you the main ingredients, is so this may still be not very thin because those paths can be very long, but now we will simply number in this branching the different FUs from left to right, and then delete every case of those numbers. So we delete, for example, you can choose K being 1 over epsilon. Let me choose K being equal to 3 here, for example. And I may then delete every third one. Let's start with 1 mod, all that are 1 mod 3. So I will delete the one numbered 1, then I will delete those that are numbered 4. And after I do so, first I delete only a small fraction, and then the remaining components will be small in terms of number of colors that are on the path, And the previous results will help them to lead to a constant thinness in those components and will prove the decomposition theorem. I know this was quick. I'm more than happy to explain more in detail. I also think it's not unlikely we will probably talk about that in one of the workshops again later on during the same trimester. So I'm happy to explain also more there. And last but not least, it turns out one can actually do a local search approach that gives you 1.5 by so one issue with the relative greed is, as you saw in the explanation beforehand, we was in the analysis beforehand, we only improve on the uplinks. We disregard the other links that we already included. But what one can do is one can actually also show how one can improve on those and extend the analysis by using a concept called witness sets coming from Steiner tree. And this will lead to a local search procedure that also can improve on links you added previously that were not uplinks, leading to a 1.5 approximation. And what is nice is that that procedure also gives another approach. If you apply it to Steiner tree, you can get another natural log of 4 approximation, logarithm of 4 plus epsilon to be precise, which is the currently best factor through a local search procedure, and this matches the 2 other algorithms that are known currently for that, or at least one algorithm with 2 different ways to analyze it that are known for that setting. But it's somewhat different, and also it's, by the way, gives the guarantee in a natural LP. So it's some nice consequences for Steiner tree too, but I don't have time to get into this now. Let me finish here. So I skipped the local search part, and just want to finish with some questions or some potential open questions that may be of interest. So it's interesting, as I said, this also works, there's an idea then to go from relative greed to local search, and works also for Steiner tree, but it seems to be quite general idea. Maybe there's further applications we don't know about. So the approach here, at least the tab approach, the W tab approach, is not with respect to an LP. It would be nice to have a nice LP relaxation, an actual one, that has a small integrality gap. I mean, one can always cook up LP relaxations by using the equivalence between optimization and separation, but of course, it would be nice to have a natural LP relaxation that's strong. I have to admit, I never thought much about node connectivity. We talked about edge connectivity here. There's already some interesting work on that topic too, but maybe some of those techniques here would just extend to that case. I'm not sure about it. There's other questions about trying to beat some long-standing factors. For example, now we could try to work on beating factor 2 for weighted connectivity augmentation, so not tree augmentation, but connectivity augmentation. So this would be weighted cactus augmentation. That remains open. Maybe a similar relative greedy approach could work out. There are additional hurdles, but it would be interesting to know. And another problem is the min way to edge connected spanning subgraph problem, for which we also just know a 2 approximation so far. It would be nice to have better factors. Hopefully some of those techniques can help, but of course we don't know. Okay, thanks a lot for your attention. Sorry for a little bit of extra time I took.